Hello students, in previous video we have seen how Cartesian and polar coordinates for two-dimensional plane are defined and how they are related. Now in this video we are going to generalize those concepts that we have seen in two-dimensional plane to a three-dimensional space. So first we will start with Cartesian coordinates in 3D. So for Cartesian coordinates in 2D, we have drawn a rectangle whose one vertex is given point P and the diagonally opposite vertex is origin. Now we will generalize that for 3D. So suppose we have this point P in three-dimensional space. So we are going to give its location or coordinates with respect to, let's say, this point O. Now here we are going to draw a cuboid or a box, that is a generalization of rectangle in 3D, such that whose one vertex is P and the diagonally opposite vertex will be this point O. So let us take this as our x-axis, this as y-axis, and this as z-axis. So box or cuboid whose one vertex is O and the diagonally opposite vertex is P is this. So you can see here this O and P, they are diagonally opposite to each other. So here this distance along x-axis, we'll call that as length. So this length is x. Distance along y-axis, we will call that as width, and the distance along z-axis, we will call that as height of this cuboid or this box. So therefore the coordinates of this point P are x, y, z. So this is how Cartesian coordinates for 3D are defined. Now we will see how spherical polar coordinates for 3D are defined. So in spherical polar coordinates, we are going to generalize the concept of polar coordinates that we have seen in two-dimensional plane. So here again, let us take a point P in a space, and we are going to give its coordinates with respect to, let's say, this point O. So here we are going to generalize the concept that we have seen for polar coordinates. So in polar coordinates in 2D, we have drawn a circle whose center is O and the circle passes through point P. Now here we are going to draw a sphere whose center is O and which passes through point P. That means this point P will lie on the surface of the sphere. So this is the sphere, and this point P, remember here this point P is not inside the sphere, it is on the surface of the sphere. So these are our, let us take x, y, z axis, which are mutually perpendicular to each other. So right now we got one information about this point P, that is this point P lies on the sphere, and let us take R as a radius of the sphere. So it lies, this R here is a distance between point P and O. Okay, now the point lies on the sphere, but there are infinitely many points on the sphere. We have to give location for this unique point. We have to give information such that this unique point can be determined. Now next, we know that sphere is made up of circles. It is a union of circles of different radius. Okay, so here, so this red line here, this is a radius vector and this is z-axis. So we will calculate the angle between radius vector and z-axis, positive z-axis. We will call that angle as theta. Now see, you got one more information. the angle of radius vector with z-axis is theta. But this will also not give us a unique point P, because for this angle, if you rotate this radius vector along z-axis by keeping this angle theta fixed, we will get this cone, and intersection of this cone with a sphere will give us this circle C. So every point which lies on this circle C will share these two properties, that the point is at a distance r from the origin, and the angle between radius vector and z-axis for that point is theta. Alright, so right now we know that point lies on this circle. See, initially we don't know anything. There is a lone point in a space. Then from radius, this r, we knew that the point lies on the sphere. Now, because of this theta, we know the point lies on the circle. But there are infinitely many points on the circle. So how to identify this unique point? So next, we will take projection of this circle on xy plane. So first we will take projection of this point P on xy plane, that is P dash, and then this C dash will be the projection of this circle C on xy plane. Now see, for every point here on this circle C, there exists a unique point which lies on the circle C dash. So if we know coordinates of this point P dash, we can easily identify the coordinates of point P. So therefore now we are in two-dimension plane, where radius of this circle C dash, let's call that radius as rho, and we are going to take angle here as phi. So here coordinates of P dash will be rho comma phi, and therefore the coordinates of this point P are r, that tells us the point lies on the sphere. Theta tells us the point lies on the circle, and this phi will give us that unique point P. So this is how spherical polar coordinates are defined. Here this theta varies from 0 to pi. Theta does not vary from 0 to 2 pi, because when theta is greater than pi, suppose it is in this side, then it will be in this side, but then we will measure angle from this left side. So this theta is always between 0 to pi, and this phi varies over a circle, therefore phi varies from 0 to 2 pi. Now we'll find the relation between Cartesian and spherical polar coordinates. So let us consider this right angle triangle ORP. O, R and P. So this is a right angle triangle, okay? The angle between this z-axis and PR is 90 degree. So in this right angle triangle, cos theta will be this height, that is z upon r. Therefore z is equal to r cos theta. Similarly, sin theta will be opposite upon hypotenuse, which is r. So opposite side means this PR, but here this length PR is same as P dash O, which is rho. Therefore sin theta is rho upon r, and that gives us rho as r sin theta. So this is a relation between rho and. Now consider this circle C dash in xy plane. So here for the circle C dash, x is equal to rho cos phi, because now our r is rho and theta is phi, okay, because in polar coordinates for 2-dimensional space plane, x is equal to r cos theta. So now here it will be x is equal to rho cos phi, because now we are taking angle as phi and this radius vector as rho, and y will be rho sin phi, where phi varies from 0 to 2 pi. Therefore the relation between spherical and Cartesian is, so x will be, so here x, so rho is r sin theta, so therefore it is r sin theta into cos of phi. Y will be rho sin phi, and rho is r sin theta, so r sin theta sin phi, and z we have already calculated, it is r cos theta. So here if you know spherical coordinates, we can get Cartesian coordinates. Now suppose we know spherical Cartesian coordinates, then how to get spherical coordinates? So this r, you can easily see this r is what the distance of this point with origin. Okay, so suppose the coordinates of this point in Cartesian, they are x, y, z. So by distance formula, r square will be under root x square plus y square plus z square, and therefore r is under root x square plus y square plus z square. Theta will be, so here we have seen that theta z is equal to r cos theta, therefore theta is cos inverse of z by r, and phi will be tan inverse of y by x. So it is from these two equations, x is equal to rho cos phi and y is equal to rho sin phi, therefore phi is equal to tan inverse of y by x. So here from Cartesian we can find spherical coordinates. So these are the relations between spherical polar and Cartesian coordinates.